All right. Almost exactly a year ago, I saw a demo of Karpenter at a conference from a fellow speaker. And this was kind of like a catalyst for something that then later turned into a joint research project between Red Hat and IBM Cloud. And today I'd like to talk to you a little bit about the whys, the whats, and the so whats of this research project, and ultimately then answer the question whether the world really needs another cluster autoscaler in Kubernetes. So we'll hear the term autoscaling quite a lot, so I'd like to begin by quickly leveling a little bit and make sure we're all on the same page here. Autoscaling basically just means reacting to workload demands with some level of elasticity, and we can generally split it into vertical and horizontal scaling, where vertical scaling or scaling up and down is making a single machine more or less powerful, and horizontal scaling, also called scaling in or out, is then adding or removing more machines. But why does it even matter? If it works on my machine, surely it'll be fine in production, right? There are three main reasons, really. On one hand, end users are impatient, and if millions of people want to buy the Taylor Swift tour tickets, the website has to keep up. And if it can't keep up, then your service running on a single Raspberry Pi in some closet somewhere, it means our resources are under-provisioned. Money is also a factor, of course. If you have 6 or 7 nodes that are running at 50% utilization somewhere, you're still paying for 100% of the capacity 24/7. And in that case, you're over-provisioned. Money makes the world go round, but also nature makes the world go round. And nature thinks wasting electricity, etc., on idle compute is not cool. And the solution is to right-size your infrastructure to fit your workload's needs. How do we do that? So there are different ways to do that in Kubernetes and different autoscalers that help us achieve that. We can broadly categorize them into two or three major groups. So on one hand, we have the workload-focused ones, which are the HPA and VPA, so horizontal and vertical pod autoscalers, respectively, focusing really on the workload side. VPA is quite cool because it lets us look at the workload's historical usage data and then tune its requests and limits accordingly. And that is really great to help those kind of end users that we probably all know, nudge them a little bit into not setting really low requests and then high limits on their workloads and freeing up the cluster a little bit like that. Then HPA on its own is quite basic. It will just spawn in more pods if certain defined CPU or memory thresholds are exceeded. But we can extend that a little bit with CADA and make horizontal autoscaling a little bit smarter with external metrics. However, those are all focused really on the workloads. What I'm more interested in is the actual cluster autoscaling, so on a node level. I'm going to refer to the regular Kubernetes Cluster Autoscaler as CAS because it's just a very long word. And I don't want to say it over and over again in the presentation. And then we also have Karpenter, which is developed by AWS initially, and now it's a CNCF project as part of the autoscaling special interest group. And we'll start by looking a little bit into how CAS works and scales the cluster. So we begin our little scenario with a pending pod. So when the scheduler can't place a pod, the status becomes pending. And if it's due to insufficient resources, CAS will notice that and add more capacity as required. And CAS is really the central decision-making component here. And it monitors pending pods and decides when and where to scale. And it does so every 10 seconds. The mechanism is poll-based, so in the worst case, we already add 10 seconds to our response time here. And then CAS interacts with the machine autoscaler, which is the OpenShift term for it, and in vanilla Kubernetes, it's usually the cluster API. And this sets kind of the scaling boundaries for machine sets. And an example would be saying the machine set can scale from 2 to 10 machines. Next, we have the machine set custom resource, which manages a group of identical machines. It's kind of like a replica set, but for infrastructure. And then the machine resource is kind of the abstraction layer for the cloud provider for a single VM or instance. And then finally, of course, we have the actual nodes, so the Kubernetes representation for a machine where then our pods actually run. There are some pain points associated with this approach. We already touched upon the slow scaling speed a little bit. We noticed there are static node pools that we will require pre-configuration, and we have fixed instance types. And CAS is completely unaware of the workload requirements, so it makes these decisions based on the node groups rather than the actual pods. And that, in turn, means we will still over or under provision our infrastructure in the end. And additionally, there's no resource rebalancing, so we can't optimize our existing node utilization. Karpenter addresses these pain points in quite interesting ways, and I'll tell you a little bit more about those now. We'll imagine the same scenario as we did just now with CAS, so we'll start with a pending pod. But Karpenter is actually a little bit smarter than just polling every 10 seconds. It's using event-driven detection to see when a pod state changes and then triggers immediately on those events. And this is made possible by the Kubernetes informers pattern. It's essentially a long-lived connection that will receive instant notifications if certain events occur in the cluster. And then Karpenter uses this node pool custom resource, which is basically both the machine set and the node groups that we have in CAS. And it defines the scaling policies and node templates in one resource. And it will set certain limits for CPU replicas, and then also requirements like architecture. And this, of course, is a lot more flexible than having static node groups. Then the node claims custom resource replaces the machine custom resource. And a node claim basically represents a request for a specific node. And then Karpenter will try to fulfill that request by talking to the cloud provider. And the key difference here is also that the node claims are exactly balanced for the pod requirements. And then next is the node class, which is kind of like the cloud provider template here, and it defines the cloud-specific node configuration stuff. So the VPC, the subnets, the instance types, and images. And it's fairly smart because it will auto-select instance types, etc., dynamically. And then the nodes are just the same as with CAS. These mechanisms really make Karpenter faster, but there's even more. So we'll once again start with a pending pod. If the scheduler can place it, then it gets scheduled as existing capacity. If not, we have unschedulable pods, pending pods. And Karpenter will add just-in-time capacity, but it will also then later on rebalance if it notices that it can optimize the capacity and place multiple pods into a node that makes more sense, also like from a cost perspective. And you can make things then even smarter also with using spot instances. Now for the research project part. So I developed a Karpenter implementation for IBM Cloud, and we benchmarked it against CAS and used AWS as a sort of control group to benchmark against. The heart of the cloud provider is the cloud provider interface, which abstracts away the cloud API. We also have separate providers for the networking and instance parts, and then the IBM-specific CRDs that Karpenter would expect to handle certain life cycle operations. And finally, there's also this controller, which is kind of like a helper in all this. And one example of a function in this helper here is the gen instance types function. And it combines available instance profiles and pricing data. One annoying bit there was that the IBM APIs are a bit of a sprawl. So the other operator has to kind of mix and match some of the sources to generate the data in a way that Karpenter finds it useful. And all the APIs use different auth mechanisms, and we need separate keys. Some require to get like short-lived tokens somewhere, others don't. That was a little bit annoying. And then the AWS implementation is a lot more sophisticated because it manages more resources on the platform side, but the core functionalities really remain the same. Let's talk about the actual experiment setup for the benchmarks. So each experiment spun up 4 clusters in total, so 2 on both EKS and IKS, so for each autoscaler. We used the sort of flagship regions for both cloud providers, which is US East 1, Virginia for AWS, and US South in Texas for IBM Cloud. Obviously used the same Kubernetes versions across the platforms, and the clusters were provisioned with 3 initial nodes and set to a max of 10 nodes, mostly because my personal credit card was on the AWS account, and I didn't want to go bankrupt. And they're deployed across 3 availability zones, just like following the general best practices. The test duration was 1 hour for total runtime per experiment, focusing for 20 minutes of intense workloads to observe scaling up, and then some quiet time after to observe scaling down and see the reactions there. The 1 hour also has a different reason, mainly because AWS is really cool and will let you do billing per second, basically. The lowest unit for IBM Cloud is 1 hour. So to fairly compare the pricing metrics, it had to be 1 hour. And then we had 2 scenarios, one for homogeneous workloads and one for heterogeneous workloads. The first one was kind of to establish a baseline for very uniform workloads that are basically 4 types, some CPU intensive, some memory, network, and IO intensive ones, but there were just essentially 40 identical workloads and lots of replicas per workload type. And then for the second scenario, it was a little more erratic to actually simulate more realistic dynamic workloads. And the whole experiment was automated end-to-end using Ansible playbooks. So you could just switch out the scenario definitions in the playbook run, and then basically hands-off, let it run through. And the first phase is setting up the clusters themselves. And here we used Terraform together with Ansible. And one interesting thing here to call out is that all the cloud resources were tagged with a UUID per experiment run and with a prefix for the autoscaler type. And then this tagging is used in the end to collect the billing metrics from the cloud provider APIs. Then comes the configuration phase, which is mostly just installing Helm charts. So the different Karpenter providers, some monitoring stack, those kind of things were installed using Helm charts, also using Ansible, which is a thing you can do And for most use cases, I would probably argue against using this pattern, but in this case, it made sense. And here we just use a normal kind of Ansible loop to apply config to different clusters. And you can see we're using the kube config that the Terraform step prepared for us here. And then comes the fun part, the benchmarking. For this, we used KubeBurner, which is a tool designed to burn down your Kubernetes cluster. So it's perfect for us to simulate this scaling behavior. It's a CNCF sandbox project, and it's used internally also by Red Hat and IBM for OpenShift QA. And in code terms, the config looks something like that. It's yet another YAML file. And we can define the object templates to simulate certain workloads, and then also some additional parameters related to the stress test itself. And we have the option to create tagged runs and then also tag our metrics with that. And that also helps us later on to correlate the data to certain experiment runs. And then finally, we gather the metrics from all the different sources and tear everything down again. So we collect the billing data from the cloud platforms directly, and we collect the cluster metrics from the Prometheus. And then finally, we just do a Terraform destroy to tear everything down again. I have a little quiz question. So what do you think was the biggest bottleneck in the test process? Yes, that's correct. So the biggest bottleneck was waiting for the IKS cluster to come up. So what did we find out? What's the so what? All the data was analyzed in a lovely Jupyter notebook and produced some nice graphs. I'm showing you the graphs to prove that they exist. They're very scientific. But I want to keep it simple and focus on the more human-readable outcomes. So one impressive statistic is that on average, Karpenter used 33% fewer nodes, just in general node count terms. It was almost 50% faster in terms of node provisioning latency. And this also translates into these cost-related numbers across these platforms and scenarios. And the most impressive cost reduction was up to 33% for homogeneous workloads on AWS. IKS showed about consistent cost savings of around 20 to 23% across both scenarios. It's not as dramatic as the AWS ones, but still not too bad. And the key takeaway here is that the dynamic provisioning and spinning up what's needed when it's needed really translates into real dollar cost savings. Now, returning to the initial question, does the world really need another cluster autoscaler? It depends. So if you're running static, predictable workloads in a small cluster, then CAS is probably enough. You might not even need cluster autoscaling at all. But with dynamic workloads that you run in the cloud, those 33% cost savings are not really just nice to have, because at enterprise scale, this can add up to millions of dollars. So the real question isn't whether we need another autoscaler, it's whether your organization is ready to embrace modern cloud operations. And for those building the future of these cloud-native applications, the answer is pretty clear. Yes, we absolutely need cluster autoscalers like Karpenter. There will be a blog post about this topic. So if you're interested, you can find links to my socials on my website, and also leave you with some links to some of the upstream projects that were used, and also the repos for the experiments. And I think we have some time for Q&A as well.
Thanks. Love the talk. I think my first question was, did I get it right that for Karpenter, it isn't using cluster API under the hood? Like I have to, for each cloud, I'd have to implement a Karpenter provider, like kind of from scratch, or like, you know?
There is something in the works to make it work with cluster API.
Yes, it's interesting because when you first presented the architecture diagram, the way I expected it to work is that the machine sets would become owned objects of Karpenter, right? Like, because that's the problem with machine sets, right? Like the instance type, all that stuff is static, but it feels like, yeah, like some of this is just making it dynamic. But okay, it's a known issue, I guess, because yeah, I think as you know, right, in OpenShift and like some other Kubernetes, we support a lot of clouds, so definitely don't want to re-implement too much for each. Cool. Okay, thank you.
Great, thank you for the question.
I just have a question. Do you have a way to over-provision the nodes, like say 10% more nodes than currently is needed, or something like that, 20%, 30%?
For Karpenter, I'm assuming?
Yeah, for Karpenter.
Yeah, you can actually define your policies for how you want to scale in a pretty fine-grained way. So you can give it quite a lot of parameters for what your ideal workload distribution looks like and what the actual infrastructure is in the end.
Just sorry for being a newbie. Where can you define this? Either node pool or EC2? How do you say that? No classes. I'm not sure.
We can go back about 50 slides. So the node pool itself has the general scaling policies in it.
Okay, thank you very much.
Yeah, first of all, thanks for a nice talk. Really enjoyed. You mentioned research, so this is a part of some kind of R&D commercial research, or is it also being published as some kind of publications in impacted media or academic or scientific?
So the code part is all completely open source on GitHub, and the publishing stuff is in the works for the paper itself. So yeah, it's been like 8 months since we finished the research, but things take a little bit of time. And the follow-up was the commercial application. So there were talks with IBM to integrate it into the platform. I think we haven't heard back from them in a little moment, but that was like the idea to also offer it on their platform. Yeah, however, there was already a production deployment of it with a customer where they used that through IBM Consulting.
About a year ago, my team implemented Karpenter for one of the airline companies where we really had the spikes of the load unpredictable, and it was working much better than CAS, obviously. But what I found, what was very confusing, that at least, again, maybe it changed, but 1 year ago, documentation in Karpenter was very messy. A lot of things were changed by upstream, AWS, without any notices. And a few times when we were upgrading Karpenter, we actually had incidents, unfortunately. So my question is, how much it's more stable now? Because 1 year ago, yes, we did it, we put it in production, but we were really afraid of touching it.
So I agree with you. The documentation was terrible about a year ago. That's also what I found out when I was trying to actually write the provider, because the writing a provider section of the documentation was like to do like this. Is it stable now? It depends. It depends on the cloud platform you're using. I think the AWS version is fairly stable because they have a lot of engineers actually working on that, and it's properly productized into their EKS offering. For other providers, I know GCP has one that is in tech preview right now, so obviously we'll still have some some hiccups. And if the platform provides it officially and supports it, then I would expect it to be stable and you shouldn't be afraid to touch it.
How difficult was it to pull the data for the costing from the cloud providers in a uniform way? Because I can imagine that they have quite different formats and APIs for that, and so it can be hard to compare between the two.
Yeah, that was actually quite annoying. So the way I solved it was to just write 2 different Python scripts to then talk to the API and get that data and then convert it to a similar kind of JSON format in the end.
Yeah, sorry. I'm not very familiar with this autoscaler, but when we was some load, we would try to downscale, we would try to optimize pods to the nodes, or use smaller nodes, or group them to bigger nodes. So some of this optimization does it support?
Sorry, I didn't get the question part. Can you?
Yeah, if this autoscaler Karpenter supports some optimization when it's downscales cluster, we will try to merge pods to same smaller scope of nodes or something like this. Okay,
so Karpenter is fairly aggressive about scaling things down and optimizing its capacity and its default behavior. CAS is a lot more conservative, so you can actually see that in the node count graphs, where you see quite a bit of delay until when CAS will actually decide to scale down the nodes in its default behavior. You can also tune that to some degree, but it's never going to be quite as aggressive as Karpenter in its current state.
Hi, thanks. Do you need to use Kube the scheduler to pack the workload on the nodes to have more efficient Karpenter or the CAS, or it works this way on its own, like moving pods on almost empty nodes to another node and allow the scheduling the node itself?
Yeah, so no, it does that on its own. So no other components needed.
Any other questions? Yeah.
So you said that the longest time you had to wait until the cluster comes up in the AKS, for example. So do you have any insights how actually are the nodes booting up in the cluster providers? Is there some underlying physical hardware which has to be powered up, or how does it work?
We did observe some differences in startup times from EKS to IKS. So IKS was a little bit slower, but surprisingly, I personally would have expected it to be a lot slower, actually. But it wasn't even by that much in the end. So I guess since it's a managed service, they have quite a bunch of machines that are already almost ready to go that have certain images to run the Kubernetes services on them.
Okay, but you said, and you showed us this nice slide with the Earth, that you are trying to save the environment and save the electricity. So do you know anything about the underlying hardware when it's spinning up, how this hardware scaling works?
Can you specify what you mean with hardware?
Because usually you just start some virtual machine but it must run on some kind of hypervisor. So how the hypervisor itself scales up?
Okay, that's something I know nothing about, really. That's
Thank you.
Thank you.
Do you have an interest to try it on Azure AKS?
Try it on Azure?
Yes, because there is Karpenter provider for Azure.
Yes, sorry, you said there's no provider? There is a provider.
There is provider, yeah.
There is a provider. Yeah, there were some thoughts to also benchmark it against AKS, but for simplicity, we only did one cloud platform at the moment. But yeah, it might be interesting to do. I don't like Azure personally, so I don't.
And you have everything, so potentially I can reproduce your tests on Azure as well, right?
Yeah, it's
thank
all
you.
open source. Yeah.
There are 4 minutes left. Anyone else who wants to ask something? No? Thank you very much.